Hello guys, welcome back to my channel Gamma Di Gamma. So in the last video I believe I introduced like some final properties or applications more like it of the Dirac delta, and that I think concludes our important discussion about it. Apart from some other application in terms of physics like the electric dipole moment or the quadrupole moment tensor, we're pretty much done with the Dirac delta. So I said, just skip those applications. If I have time, I'll make a video on that in the future. But let's start, or rather continue with our discussion of complex analysis. I believe I had completed a discussion until the Cauchy integral formula and then sort of its higher order derivatives. In this video, I'm going to talk about a really important topic, which is basically Laurent series. Taylor and Laurent series. So let's get started. So let me just build your background first. Assuming a series converges, so S is equal to sum from say n equals 0 to infinity x sub n. What I mean by absolute convergence, and you might be familiar with this, people who did calc 2, sum from n equals 0 to infinity, absolute value of x sub n should converge. So that's what absolute convergence means. Now, since we have this property that the absolute value of that series is greater than or equal to the sort of the non-absolute value series. So absolute convergence is a more rigid condition than just convergence. You may know this already. If you don't, then just follow what I'm discussing. So this means that if the absolute value of a series converges, then like if you remove the absolute values, that series will also converge. This inequality is sort of because you can think about this as like without an absolute value, you also have some intermediate negative terms. But with the absolute value, all the terms are positive. So like all positive terms summed up will always be greater than like some positive and some negative terms, like some intermediate negative terms. A good example of this is the alternating harmonic series. 1 minus 1/2 plus 1/3 minus 1/4 and so on. This we know, you can use Taylor series, converges to natural log of 2, but sort of the absolute value of this series diverges. So in this case, and again, if the absolute value of the series diverges, it's the non-absolute value series may or may not diverge. It can converge, like in this case it converges, but when the absolute value diverges. And in such cases, when the absolute value sort of diverges and the regular series converges, then such series are called conditionally convergent series. Why I say conditionally is because take the case of this alternating harmonic series. There's a theorem, Riemann rearrangement theorem. You can read about this on Wikipedia. What that says is, if you sort of hand pick some positive terms and some negative terms and sum them, do partial sums individually, you can get any answer you want. So if you just rearrange the series in a certain way, you can make this converge to 5, 3, pi, any number. And Riemann said that this is true for like when sort of these conditions are valid. And again, this is I think true for alternating series. So this is just, I don't know, piece of information which might be useful to you. Now another useful tool we're gonna use actually is the ratio test. So basically the ratio of like n plus 1 term and the nth term in the limit that n goes to infinity, the absolute value of that ratio should be less than 1, then it converges. I'm gonna write this differently, ratio test. If it's greater than 1, it diverges. If it's equal to 1, then the ratio test is inconclusive, which means it may or may not converge, but the ratio test, can't give you a definitive answer. Okay, take this complex series for example. Say x sub n plus I y sub n. I'm breaking the complex series into a real series part and an imaginary series part. So S is S sub r plus I s sub I, such that S sub r is what this real series converges to, x sub n. S sub I is what this imaginary series converges to. So as a whole, this the complex series will converge, because if you do this sum from n equals 0 to infinity, we have this property. You can sort of, I don't know, use a similar logic as I used on top. And we also have this property. And again, you can do the ratio test for this complex series. And this is the condition of convergence. So I think that's sort of what I wanted to talk about. Just I want to specify that in the case of like plotting it out on a complex plane, it's going to look like some disk. It's going to be some region of convergence. You can think of this as plotting them out on the complex plane. You can think of loci of points. So for equality, it's like a circle. For an inequality, when it's like less than some number, it's going to be a disk. Okay, I think these are probably all the tools we will require for this video. Moving on. Okay, I am sure until now all my viewers are pretty much accustomed to a Taylor series. I haven't made a video introducing it. Maybe I should, maybe not. But so a Taylor series, think of it this way: c sub n, some coefficient, x minus x naught to the nth power. So Taylor series around the point x equals x naught. We need some point of expansion. So just write out some term: c naught plus c sub 1 x minus x naught to the first power plus c2 x minus x naught square, and this goes on till infinity. Now for a Taylor series, c sub n, if you recall, was 1 over n factorial nth derivative of f of x with respect to x evaluated at x equals x naught. This is a classic definition of a Taylor series. Okay, Now what about the convergence of this series? Well, what we can do from the sort of the essentials or the previous page, do the ratio test. So we have c sub n x minus x naught to the nth power over c sub n minus 1 x minus x naught to the n minus 1. We want this to be less than 1. So just simplify it a bit. Since we have this sort of polynomial, it was a good idea to use the ratio test. Sometimes it can go really bad. So you have this condition, which kind of roughly speaking translates to x minus x naught absolute value should be less than some quantity delta. And again, this is sort of jumping ahead, but I want to say that this delta depends on the expansion point x naught. This final statement I made will become a finer conclusion or a finer observation when I talk about Laurent series for for complex functions. Okay, so let's talk about Laurent series now. I'm sure this is probably the first time you're hearing about this. We all know what Taylor series are from Calc 1 and Calc 2, but we don't really know what Laurent series are. Well, it's understandable because they are actually sort of a topic in complex analysis. So, say you have f of x, which is, instead of starting with 0, you start from negative infinity to infinity. So c sub n x minus x naught to the nth power. Now I'm going to write some terms, and this looks like, well, we start from negative infinity, so we're going to have some dots. Minus c minus 1 term, and x minus x naught to the negative 1 power, which is x minus x naught in the denominator. Let me just start with x minus 2, and then the negative 1, and then the 0 term, which is the polynomial part is 1, and the first term x minus x naught, second term, and so on to infinity. So if you notice, what's sort of different in the case of the Laurent series is that we have these negative power terms. The Taylor series, you can think of that is as a special case of the Laurent series in the regards to the fact that the Taylor series just has positive power. So if you set all the coefficients of the Laurent series which are which are associated with negative powers to 0, you're basically going to end up with a Taylor series. Now the convergence for this guy is actually a little tricky. The thing is, we have to do 2 ratio tests for convergence. So one for the negative and one for the positive parts, the powers I mean. So one for like these, and then the other for these positive in the numerator. And the convergence condition, I say, is tricky because it's sort of, I'm not gonna like derive it or anything, but it's going to be x, absolute value of x minus x naught is going to be between delta minimum and some delta maximum. And again, it depends on x naught, which is your expansion point. And the intuition for this that I would like to give you briefly is that if like x minus x naught is too small, then the higher negative powers or the powers which basically are higher in magnitude on the negative scale, they're going to, if it's small, they're going to like blow up as we approach negative infinity, right? Something that's small in the denominator like blows up eventually if you like keep raising it to higher and higher powers in the denominator. And again, less than delta max, because that's for the positive part. We don't want the x minus x naught to be really large, because like the positive powers are going to basically make it blow up quickly. So we need to find that sweet spot between some minimum and some maximum value. That's why it's a little tricky, and that's why we don't really cover it in elementary calculus or basic calculus courses, because of this delta minimum. And again, we don't even see the applicability of this Laurent series expansion for real valued function. I'm just writing it down for now so that you get an introduction to this. Now, another property that's going to be extremely helpful for us is this geometric series. The sum of terms in an infinite geometric series is just going to be this. You can write some terms out: 1 plus z squared plus z cubed, and so on, where z is like the common ratio between terms. If you notice 1 and z, you divide consecutive terms, you get z out, so that's the common ratio. And this again holds true when absolute value of z is less than 1. Again, this I'm saying z is a complex number, so the absolute value is really a magnitude of that complex number. A sort of a general formula for sum of finite terms of a geometric series. I won't derive this, it's really easy, not really hard to derive, is 1 minus z to the m plus first powered over 1 minus z. Now, if you set the magnitude of z to be less than 1 and you set m to infinity, you're going to kind of derive this formula for infinite geometric series summation. So these guys are really important, and we're going to need them for a complex Laurent series. See you on a fresh page. Okay, to start our discussion, let's have some a complex function, and I've talked about these in several videos earlier. Let's assume it has some Laurent series expansion form. So just writing it in a general form, z minus z naught raised to n. So I'm expanding the Laurent series around the point z naught. Okay, assume f of z is like a simple function of 1 over z minus a. Function with like a simple discontinuity at a. Okay, so what do we do? Well, what I actually want to do is actually use the Cauchy integral formula, such that f of z, I can write that as 1 over 2 pi I closed contour integral dz prime f of z prime over z prime minus z. Now let me just define the contour. Again, it should ideally be a circle. My drawings is bad, can't help that. So I'm going in the clockwise direction for convention's sake. Assuming that the central point is z naught, the point around which you're expanding. It makes sense to have a circle centered at z naught because we're expanding around z naught. A, assume it's like some point that's inside. And z prime is basically some point along the contour. And then z just becomes like some point in the interior here. That's my contour C. Now the issue is this sort of discontinuity at A, this pole at A. So what we're going to do is we're going to deform this contour such that now we have, let's see, this is outer region. trying my best to draw here. So Z prime is like on this. Entire thing is contour C, but specifically this outer contour is C1, this inner guy is C2, and we're sort of going in this direction, going anti-clockwise, going inwards, then along C2, and then sort of outwards, so that it's a closed loop. And we again taking the limit that this gap between them is 0. I'm just drawing it because I want to show clear contour deformation. Z0 is again inside. A is somewhere here along this sort of dotted line. Okay, this is sort of my deformed contour, and I'm gonna actually integrate over this. I broke C, I have written it as C1 plus C2. So now let me just sort of substitute that in this equation. I've done this because now instead of just like the contour integral, if you do this contour integral, it's sort of gonna correlate to the points enclosed inside, right, using the Cauchy integral formula. But in this case, the sort of the closed region is going to be this guy, and that does not have singularities or poles. So instead of like having the entire thing, I'm just broken it down. I want to sort of avoid these poles, like the one at A, as much as possible. And you'll see in a bit why I'm kind of doing this and why I'm also sort of skipping over Z0. Okay, so f of z now can be written as this deformed integral of the two contours, C1 and C2. So C is broken up into C1 and C2 by deformation. So C1 is basically dz prime f of z prime over z prime minus z. And then for C2 we're going to take a negative, because notice it's in the clockwise direction against our predefined convention. Okay, now what I'm going to do is I'm going to like add and subtract a point, the central point z0, in the denominator of both these guys. So I'm going to have f of z prime and then z prime minus z0 minus z minus z0. So if you just expand it out, it's like adding and subtracting the same quantity. So dz prime f of z prime over, well, do the same thing, z prime minus z0 minus z minus z0. And now I'm gonna do a weird thing. I'm going to actually take rewrite this a little bit so that you clearly see what's going on. F of z prime over z prime minus z0, and then sort of factorize that term out. So I have 1 minus z minus z0 over z prime minus z0 for C1. For C2 I have, I'm sorry for if it's sort of squished together, dz prime f of z prime. I'm gonna take z, factorize z minus z0 outside, so I have, I think, well, that negative and this, you sort of reshuffle the denominator, you get a positive here. 1 minus z prime minus z0 over z minus z0. Well, now one clever observation is that on C1, on contour C1, which is the outside contour, z minus z0 is less than z prime minus z0. We can see this, z minus z0, z is like some point that's going to be sort of inside. inside this region. Z, so that's why defining the region was important. Now Z is going to be inside. Alright, that's how the Cauchy integral formula worked, and you clearly see why we sort of deformed the contour, because now Z will never be Z0 or the singularity point or the pole point. So Z, you can see Z minus Z0, which is this distance, is less than Z prime minus Z0. Now Z prime, in the case of C1 integration, is this guy outside. This distance is less than, well, this distance. It clearly makes sense. You can sort of do some Euclidean geometry here, make sense of that. So and that's why this denominator part 1 over 1 minus Z minus Z0 divided by Z prime minus Z0 can be written as a geometric series with common ratio this guy, the thing I've bracketed out. So n equals 0 to infinity. The common ratio Z minus Z0 over Z prime minus Z0 raised to the nth power. And again, I can do that because you can check for the sort of the condition that the common ratio magnitude has to be less than 1. You can check that Z minus Z0 over Z prime minus Z0 magnitude is less than 1, which also implies that Z minus Z0 is less than Z prime minus Z0, which is a valid condition on C1. We just sort of wrote that, taking some insight before. Now it clearly, we clearly justify this factorization, because once we have this sort of term in the square bracket, we can write it as a geometric series, justifying that the common ratio is always going to be obeyed. So this expansion will always hold true on C1. So always true on C1, and that's more than enough because we only integrating on C1 for the first guy at least. So let me just like write the first term. So the first term is 1 over 2 pi I. Sum from n equals 0 infinity. I believe we have contour integral C1 dz prime f of z prime, and then sort of this guy over here. So it's going to be z prime minus z naught raised to n in the denominator, and there was already this same thing, so this and an nth power, n plus first power, and then this numerator, which is sort of independent of z prime, so you can take it outside the integral to get z minus z naught to the nth power. That's the C1 guy. Let's try to do a similar thing on C2. Okay, so let me see. On C2, we have the condition z minus z naught magnitude greater than z prime minus z naught, sort of the opposite of this guy. Let's check that out. Z minus z naught is going to be, I don't know, let's take another side. Say z is like here, again inside the region, shaded. This z minus z naught, this distance, is greater than z prime minus z naught. Now z prime for the C2 integral is going to be here on the C2 contour. So you see z minus z naught is always going to be greater than z naught and z prime the distance. So it's sort of the opposite of like the red condition, the condition for contour C1. And we sort of have this in the denominator, right? We can try to do a similar thing. 1 minus z prime, so 1 over 1 minus z prime minus z naught over z minus z naught, I believe is the right expression, is going to give us sum from n equals 0 to infinity. Again, infinite Taylor series. So z prime minus z naught, or z minus z naught, the common ratio raised to the nth power, or the power of the index. Again, this holds true as long as z prime minus z naught over z minus z naught the magnitude is less than 1, which roughly translates to z minus z naught being less than z minus z naught, which is precisely the condition on C2. So it always holds true on C2, and that's more than enough. That's more than what we can ask for at this point. Let me write the second term in. So the second term, so for this expansion, and again, you clearly see why I took z minus z naught outside. So I got this denominator, which I could write as a geometrical series and sort of get like a nice simplified form out. It's all about finding this distance, or which inequality is satisfied. I have 1 over 2 pi I. I will be summing n equals 0 to infinity. Integral over C2 dz prime f of z prime. I will have a z prime minus z naught term in the numerator. So z prime minus z naught. Let me take different indices just for avoiding confusion. To the mth power, and then all of this, square bracket this out, is divided by z minus z naught m plus first power. You can clearly see that we have a z minus z naught and then, well, z minus z naught here. So add the powers just like we did here, except it comes out the integral because there's no z prime dependence. So this is a little long expression. I hope you like see the logic behind it, and I hope this like convinces you. What's so great about this? Fine, we use some Taylor series because we use some infinite geometric series formula because it was working in that contour. What's the big deal with that? Now here's the big punchline. The punchline is, well, f of z, you can sort of re-index everything. So the positive terms just remain the same. Contour integral C1 dz prime f of z prime over z prime minus z naught n plus first power z minus z naught to the nth power plus, well, n, you can let that n start from -1 and go to negative infinity. I'm just re-indexing everything. Integral over C2 dz prime f of z prime z prime minus z naught the n plus first power z minus z naught to the n. So you notice what's going on here. There's sort of different expansions for positive n and for negative n. Well, Cn, that's what the coefficients were, the way we defined everything. You can write this, split the positive and negative, C sub n z minus z naught to the n, and minus 1 negative infinity. It should actually be opposite, but whatever. C sub n z minus z naught to the n. You notice this you can compare the forms, this form and this form, and compare the coefficients. You get Cn 1 over 2 pi I contour integral over C1 dz prime f of z prime over z prime minus z naught n plus 1 for n that's greater than or equal to 0 for the positive case, positive semi-definite case to be precise, 1 over 2 pi I C2 dz prime f of z prime minus z naught to the n plus 1 for the negative definite case. So what I can do is I can generalize all cases to say 2 pi I contour integral over c f of z prime over z prime minus z naught to the n plus 1. This is the most general case, and that's how you this is the general formula for the coefficients of a complex Laurent series. Now the convergence is something we should talk about in the future, and we will. One thing that's interesting to notice is that this guy, the first term, is actually using the nth derivative of the Cauchy integral formula, just 1 over n factorial, nth derivative of f of z with respect to z, evaluate z is equal to z naught. So you clearly see that the positive part of this Laurent series coefficient is actually the coefficient of the Taylor series. So you see the positive part of the Laurent series is the Taylor series, which a fact that will actually remain pretty true. Again, the way I generalize it with a contour integral over c is using the assumption that any person who's calculating these coefficients knows how and when to deform the contour. The contour deformation we did was just because we assumed that f of z was of the form 1 over z minus a. In general, it would have been a little hard to see, but that's why it helped us to generalize to a formula, which will sort of we will have to be a little versatile with it, which will sort of change depending on what singularities are inside the contour, which are not. And I'm gonna do a big comprehensive example of two singularities and sort of give you an idea of where the Laurent series is purely a Taylor series and where a Laurent series is purely a series of negative powers, and when and in what region a Laurent series is a proper Laurent series with Taylor series and negative power series. So that's where we will actually think about the regions of convergence in the next video, and sort of get an idea of the dependence on the point of expansion z naught. So we'll actually see these or visualize these things in first person. I hope you'll stick with me until then. I hope you understood whatever I've done. Explanation might not have been is not really rigorous, but I think it gives you a really good idea of what's going on here. It doesn't require big things. It just requires a formula for summing infinite terms of a geometric series and some basic algebra, and I think that's it. And then observations for the Cauchy integral formula. So yep, I think that's it for this video. Please like, share and subscribe to my channel, guys. Recommend me to your friends. I'm going to actually continue with this complex analysis video series. I'm not gonna break like I did. Apologies for the inconvenience. I'm gonna do this till the end and reach residue theorem, which many of you wanted me to prove. So I hope you stick until then. Stay tuned for more content, and peace out.